Hello everyone, this is Yalishetty Priyanagasai, EB from EB11, E20CSE188. I study in Bennett University, and today we will see the implementation of multiplication of vector and a matrix using CUDA Python. This was an assignment for us in our course of high performance computing. So for today, the problem statement is write a CUDA Python program to implement the multiplication of a vector and a matrix. Some tips and instructions to follow that were given to us is to consider a matrix size sufficiently large of approximately 1 lakh. Measure the performance of the sequential version and the optimized parallel version. Also calculate the speed up that is observed in this entire problem. So in the solution, first let us import all the necessary libraries that are required for this lab assignment. First, we are importing NumPy as NP. NumPy is a library used for a variety of mathematical operations on arrays, matrix, and vectors that provide an efficient calculation. It also provides high-level mathematics function and adds powerful data structures to Python. Next, we will be importing Numba, which is a just-in-time compiler for Python. It is best in use when dealing with NumPy loops and functions. It is called using decorators, mainly @JIT or @NJIT, which we will be using today. As you can see here, we're importing it. And also float64, which is basically telling the structure which will be data type which we'll be using. Then Numba basically executes the function by converting into machine code by using the just-in-time decorator for execution, and then runs the code at native machine speed. So it basically increases the speed as it is directly converting it into the machine language or machine code. It works on operating systems, Linux, GPUs, CPython, and NumPy. It is a core package and it is best for numerically oriented code. Pandas library is not understood by Numba. Then we are also importing time to measure the performance and to calculate the speed up. So let us run this. So now we will be creating a function to calculate the vector matrix multiplication from scratch. So this image, which I have gotten from this link, shows how matrix multiplication actually works. Here, if you take A, B, C, D, E, F, which is your matrix, and G, H, which is your vector. In multiplication, we multiply A with G, and then we sum it with B and B multiplied by G, B multiplied by H. I'm sorry. And this is how you get like a 3-row matrix as a solution. So if we go with that, now this is how we are implementing the sequential function. In this, we will be taking a vector and a matrix as an input, and we'll be calculating the number of rows and number of columns for that particular matrix which we've gotten here. And we are also initiating a matrix with zeros for the final output that we'll be getting. And in this, we first start iterating through the row and through the column, and then we multiply as we have done it here, A into G. That's exactly what we're doing here. And then we add it to the add variable that we have started here. And then we tell the function to input that thing that you've got into the results matrix here, which we have created using the np.zeros. And in the end, we'll be finally returning the result. This is just the implementation of this image that you can see on top. So this was our sequential way of doing this. Now, if we go to the parallel version, here we'll be using njit, which is from Numba. And in this, we'll be using parallel is equal to true, uh, which results the automatic parallelization of this function. And float64 is basically the data type so that the memory allocation is perfect. So in Numba, we have something called as no Python mode, which uses @JIT, which operates in two compilation modes, the no Python and the object mode. The no Python mode essentially compiles the function, so it runs entirely without involvement from Python interpreter. This gives us the best performance. Uh, so this can be written in two ways, where you write JIT and then you say no Python is equal to true, or we can use ngit, which also signifies the same, where we are telling our compiler to not fall back into its default way, which is uses object mode if no Python mode fails, so that we get the optimized thing. And here we are using parallel is equal to true, as I said, for initiating the parallel process. And float 64 is basically we are typecasting our input of vector and matrix so that we have proper memory allocation to again increase the performance of our function, which we are making in parallel. So um, let us run this. So we are also using ngit here, as we have already discussed. And these flow 64, this is the output data type, and these are your input data types, where this is a 2D matrix and this is a single vector. And we are doing ngit on multiplication, which is the function that we have received from here. Now, we were also required to create a function called as the validation function, where the validation function basically checks if the result of the multiplication function that we made on top is correct or not. Now, because the ngit basically converts your function into machine code, there might be instances where it is giving you an different output from the one that you received with the normal Python interpreter. So this function basically uh, validates if your output for both the normal Python compiler and the ngit compiler has compiled the same output. If it does, it returns true. Otherwise, it returns as false or gives us an error. So now, as the tip was given on top, where we have to make a matrix of very large sufficient size, here we have made a matrix of 10,000 or 10,000 input, where we are using the random input variable to create it. We're also using a vector which is significantly very large, and this is the input that we'll be using. And as written above, these are basically your double end numbers. So now to measure the performance of sequential and parallel. So this is something that I have gotten according to the Numba's guide. So this is Numba, this documentation. This is the official site for Numba. And this one is just a 5 minutes guide to Numba, where it explains everything that I already told you about. You can go through this. And so basically, if you see here, it shows how to calculate the time. So they have clearly mentioned that the Numba compiler takes more time in the beginning because it has to compile it for the first time and convert it into machine code. But after that, it does not take a lot of time because it will be saved into your cache memory, and because of that, it runs much faster. So that's what we do here. We are going to run it for the first time, and we will not be considering this time for us because this one includes the execution time it took. So this is with the compilation time. This one right now it's going to take a while because this is converting it into the machine language. And also this one is the sequential version, so it'll be taking more time than the parallel version. As you can see, for the first time, as it is written here, it took a lot of time because it has been compiling. And next one just came out in a millisecond because it gave you the result from the cache memory. So as you can see, this is a almost 5 times difference In fact, more, because this one is coming in nanoseconds and this one is in milliseconds. And to get an average of this compiling and execution time that it takes in the thing, we use percentage time, which gives us output very detailed, and it executes our function multiple times and gets the average of that time for us to get a very accurate uh, picture. You can also calculate the average time for just the execution instead of just also including the composition time. So let us also look at that. So this one, it says that it took 46 seconds. And as you can see, if you remove the entire compiling time it takes, it is giving us less than 7 nanoseconds. So same we'll be calculating for parallel. Here again, we're doing it without execution. As this is parallel, it took way less time than it did before. As you can see, this one had taken us 45 milliseconds, or 45 seconds in total, whereas this one just took us 0.919. And now if we see the actual time it is going to take us, it is taking us less than 8 nanoseconds. Again, to get the average of compiling and execution, it has taken us 193. And if you want the time of just execution and not the compilation, let us find out. It is giving us 10, which is very less time, as you can see. So let's also validate the result that we're getting. For our basis, we can see that this array, as you can see here, it is same as this array that we have here. So that is what basically our validate function does. It sees if the answer we have gotten from basic multiplication function and the ngit function is same or not. In this scenario, as it is the same, it is giving us the output as true. Now let's calculate the speed up between the parallel and execution time. So this is the average time I've gotten after running this entire notebook couple of times, and this is the basic average time that I've gotten, where the sequential takes about 48 seconds, whereas the parallel takes about 0.18 seconds on average. So let us see, the speed up is almost like 250 times. So as we have seen from now, the entire conclusion is basically we have used ngit from the Numba library. There are other decorators as well from Numba, which are JIT, ngit, vectorize, GU vectorize, stencil, JIT class, cfunc, overload, etc. They can all be found on their website as well, where you can see it here. There is documentation for each of them. JIT and ngit are basically the same. JIT basically has that thing of falling back onto its object mode, where it can use the Python compiler in case there is no support from Numba. Numba has a very limited support for a lot of things. Like it does not support pandas, or it does not support dictionaries. So in that case scenarios, generally the Numba compiler does go back to its no object, like the object mode, which uses Python compilers instead of ngit. But this reduces the performance of ngit. Then vectorize and all, you can see there are documentation for each and every one present here. Then parallel is equal to true, as we have seen that it enables the automatic parallelization of the function. This is done on its own, which is why we haven't made a custom kernel for the same, because this itself gives us about 250 times the parallelization. You can see more stuff here. And yes, so as I have said, the average time it takes is 48 seconds, but this one takes only 180 milliseconds. And we could also see the speed up was more than 250 times, which is a lot. So thank you so much for listening, and I hope I made all the concepts very clear. Thank you.